In this video we're going to talk about how to make transmission lines on an RF PCB, and about some design considerations for those transmission lines. The stack-up of a PCB is at the heart of designing a transmission line because the separation between layers trades off between capacitance and inductance per unit length in a wire. The inductance per unit length is proportional to the amount of flux coupled in a current loop, and the current loop is formed by the forward and return current in a printed circuit board, which I've shown over to the right of our top view of a trace. Wider separation allows more field between the forward and return current, but also results in electric fields becoming weaker as the plates move farther apart. So the increased field increases inductance, but the weaker electric field reduces. The increased magnetic field increases inductance, while the reduced electric field decreases capacitance. Similarly, trace width affects both capacitance and inductance. Wider traces mean more electric field is coupled between the plates as you get more parallel plate area, but it means that the magnetic field becomes weaker around any given amount of current. These effects are captured for... You can combine these effects to calculate the characteristic impedance of a microstrip equation, and the equation that does that is shown on the right. The ratio of trace width to stack-up separation appears prominently in these equations as this sort of H over W effective ratio, which shows up twice. So this is one equation for microstrip impedance out of many, because there have been lots of approximations that have been developed over the years. My usual approach to sorting through all of these equations when I'm designing a microstrip transmission line is to pull all of the online microstrip transmission line calculators and pick out the mean of their slightly varying answers. Now, this microstrip is one way to build a transmission line. It turns out there are many others, and you should familiarize yourself with the profiles and impedance formulas for strip lines and coplanar waveguides, both of which can be useful. We've talked a lot on this slide about how to make a transmission line, but not really about why you would. Certainly, you can use a transmission line to connect RF components, which is most of what we've talked about in this class. But transmission lines are also sometimes useful for high-speed digital signals, because the high-frequency content and sharp edges of digital signals can reflect off of unterminated receivers. So if you're doing that, don't forget that you need termination resistors, and you'll often have to design those yourself, because digital circuits usually try to maximize how fast they can go by minimizing their series impedance. So sometimes you need to add those explicitly. There's lots of debate in the community about whether it's important to have termination at your digital source or at your digital load in order to match the transmission line, but you're going to minimize your reflections and have the most consistent performance if you terminate both sides. When you're drawing transmission lines or any kind of high-speed wiring, you're going to run into very strong aesthetic preferences in the radio frequency circuit board design community. And those include things like your wires should be straight, and that you should never make 90 degrees turns with high-frequency wires. Many of those design recommendations aren't grounded in solid physics, but I recommend you follow them anyway. It produces nice-looking boards, and it forces you to think carefully about floor planning when you try to follow those recommendations. And it also keeps people who really believe in them happy, so you don't have to get into too many arguments. But like I said, most of these design practices are myths. They won't have a significant effect unless your signal is in the high tens of gigahertz. So here are some specific arguments that you're going to hear. Most of them come down to the idea that corners in a wire have extra capacitance, because the fringing field coming off of the transmission line on the vertical wire and the horizontal wire will add up inside of the corner, and that extra bit of field density looks like a bigger capacitance. So that's true, but it's really a pretty small change. And one way you can evaluate whether that change would matter to your wave is to kind of compare your wavelength to the width of the trace. If your wavelength is significantly longer than the width of the trace, then that sort of discontinuity is going to appear electrically small to your wave. And if your wavelength does get to the width of the trace, then you probably have other problems like the skin effect, which is a phenomenon where high-frequency signals cause current to crowd at the edge of traces, changing their resistance. So because corners are frowned upon, jogs are doubly frowned upon because they have lots of corners. But if you accept my argument that corners don't really matter that much, then jogs also don't really matter that much, because lots of corners still have no effect. Now, if you don't want 90-degree corners or jogs, the way you can fix that is with chamfers. You take 45-degree turns with your wire instead of 90-degree ones. And that's what most RF PCBs have on them, and is a sort of common stylistic convention in designing them. On the other hand, putting wires too close together is really dangerous because signals can couple from one wire to another. Signals with fast changes in voltage can capacitively couple to adjacent traces, and you model that with a capacitive divider. And they're especially likely to couple to traces on another layer, like this one. So the orange layer on top can couple to the pink layer underneath, because they have like a direct parallel plate capacitance between them. In addition, if you have high current or high fast changing current flowing in a trace, that shoots out sideways between the trace and the ground plane, and it can couple into other traces that run nearby. So you'll model that with some sort of mutual inductance between the traces. So pay really careful attention to your trace spacing, especially on high power or fast switching traces. And there's one other sin that I've shown on this slide that you need to be really careful of. The wire on the top layer crosses over a gap in the ground plane and a trace underneath. So in addition to coupling to the underlying trace, this has the result of breaking up the current return path for the trace on the top layer. That adds a lot of parasitic inductance to the trace because you wind up with like a big loop in your current path that can couple a lot of field. And it also makes the underlying break in the ground plane into a slot antenna that'll radiate when you drive the top layer. So in general, breaks in the ground plane are very dangerous, and you should only use them if you know what you're doing. So in summary, trace width trades off inductance and capacitance per unit length, which means that it determines your characteristic impedance. And your stack up is of course an important part of that too. And corners don't really matter in traces, but coupling and multi-layer crossovers do.